the density itself. So it means that you can determine density field. Okay. So if we can make a small recapitulation, we saw Shadowgraph, which is based on change of position where light impact your screen, and it's possible to derive that this corresponds to sensitivity to the second derivative. Then we saw Schlieren, which is based on change of the angle under which your light impact the screen, and it's possible to derive that this corresponds to the gradient of density. And this one is based on time delay, and it's again possible to derive that this corresponds to sensitivity to variation of density itself. Okay, so for this you need basically two parallel beams of homogeneous light which are in phase, and then one beam serves like as a reference, and one beam goes through your test section. Okay, and then we need to combine these two. And then if you have density variation in your test section, it means you introduce certain time delay. Then after combination you will see interferogram, or you can see these interference fringes. Okay, because you introduce certain time delay. Okay, and then if you know wavelength of your laser, then you can determine density step between two fringes. Okay, and then if you know density at certain location, then you can really count and determine the rest. Okay. Okay, then there are like two main setups of interferometry. One is Mach Zehnder, which is very difficult to set up. It's very sensitive to vibrations. It requires really high quality of optical elements, and basically it's arrangement of light splitters and mirrors. I mean, the goal is clear. We need one beam, which is our reference, and one which goes our test section, and we need to combine them afterwards. Okay, but since it's really sensitive, you need, for instance, to use also the same side windows as you use for your test section, also for the reference beam, because you need to ensure exactly the same optical path for both. Okay, so very difficult to set up. So another option is to use so-called holographic interferometry. It's this example here. So you use basically a laser which illuminates your test section, and also directly this photographic plate. Okay, then you acquire one image without flow and one with flow, and then you can combine them, and this creates your interferogram. And you can see it here, because it's a hologram. Then we can rebuild this interferogram, because if you use the same laser as during the test under the same angle, then we have here the camera, and we can see our results. So the results of your measurements are stored in this photographic plate. Okay, and since just a second, since it's a hologram, then of course we rebuilt this interferogram at the position of the flow, right? So it means that our camera is focused not on the plate, but somewhere here. You can see my hand, which is now sharp. So it means it looks at this position, somewhere at this position. Okay. So it means during the test, the flow was somewhere here with respect to this plate. Okay, so because it's a hologram. I mean, it's difficult to explain with hands here, and then you need to go through your notes. I mean, you have a lecture, notes from lecture series. It's explain that. Okay, so this is an example from turbo machinery. So you can see the trailing edge of a blade. Then you have wave, our reference probe. Of course, in order to know the flow properties at this point, so it means also density. And then if you know the wavelength of your laser, then you know delta rho between two fringes, and you can count and determine the density field. Of course, a priori, you don't know if you should count up or count down. So for this, you need to have some knowledge about your flow, like you see that, okay, these are shocks, then I know where temperature goes, or here you have wave, and so on. Okay? So now questions. I mean, you had. I'm sorry, you had questions. You forgot.
The thing is, something I don't fully understand is that actually when you're doing the interferometry is between somehow a picture you've taken before and then you're making the experiment. So if the environment setup changes between those two configurations, then somehow the interferometry will be wrong.
Yes.
Or correct?
Yes.
Okay.
So it's complicated stuff. Okay, there are plenty of possibilities. So for instance, for Mach Zehnder, you can continuously see during the test your interferogram, because you in real time combine these two beams. Okay, so you can really see on the screen your interferogram in real time. In this way,
you have only one beam.
You have one beam, and then you acquire without flow and with flow. Okay. Of course, you can't change your setup between these two. Okay. And also you have more options. One option is to use the same photographic plate for both. So you need to set up a mirror. So in this way, you let's say illuminate your test section and also the plate. So the plate kind of receives light from the laser and from the test section. Okay. Other option is indeed to use two plates. One, and you acquire without flow, with flow, and you really stick them together, and this creates your interferogram. Okay. So there are plenty of options. Okay. So we could spend a whole day at least for this. For instance, one thing, there are two main kinds of interferometry. One is so-called finite and infinite interferogram. So basically, infinite one, it means that there is initially no angle between your beams. Okay. So without flow, you can't see any interference fringes. Okay. So and then you blow, and this interferogram appears. Okay. So in this case, this density difference between two fringes is fixed, and it's given by wavelength of your laser. Okay. Then there is another one which is called finite, and it means that there is a certain angle between your beams, and in this way you can play with this angle, and then you can really change the resolution or change this delta rho between two fringes. Okay, so for this finite, you have interference fringes even without flow due to this angle, and flow will just change their pattern. Okay, you see, but you have one more degree of freedom how to change the resolution of your interferogram. Is it clear? Like this? Go through notes, and then it will be more clear for you, I'm sure. Okay? Do you have questions for this? Okay, it's almost time for the next one, so I will release you for your next lab. And I hope you enjoyed it a bit. And, you're welcome. I don't know